Okay, this is ELEC142 Problem Sheet 5, and this is answering question 3. This is quite a long question, so it's going to have its own recording. In this question, we've pulled quite a lot of things together. So first up, part A is actually computing the values for an AC circuit. We've done this before. This could really be in an earlier problem sheet. The stuff we're doing in part B, which is looking at the instantaneous power at a specific point in time, is much more relevant to the power that we've been doing. But it's what we're going to see is that you need to do the analysis before you can then look at the power values. And then finally part C is going to replace the inductor and the resistor with a single complex impedance, which is what we were doing in problem sheet 4, which is the one just before this. So this is pulling quite a lot of different things together. It's going to take quite a long time. So part A is going to take about a page to work out. Part B is going to take about another page, and then part C is going to be quite short. We'll work through it step by step, and if you can do this, you're well on course for the sort of question you may face in an exam. So first up, let's calculate the correction on this. Omega, the value of omega is 500 radians per second. If you don't have this value, you won't be able to complete the question. So please note the correction on that. I have also put that on Vital for you to see. So let's have a look at how we solve it. First up, we're asked to find the expression, the circuit current I of t. So let's begin at the beginning. So we know from Kirchhoff's voltage law that the total source voltage here, which is 30 volts at an angle of 0 degrees, we can assume it's 0 degrees because we weren't given anything in the question, is going to equal the voltage across the inductor plus the voltage across our resistor. So that's all I've written here, is V is equal to VL plus VR. So let's start putting some values in. Well, we've got the value for the source voltage. It's 30 at an angle of 0. That was in the question. I've just converted it directly to polar form. So let's look at the voltage of the resistor first because it's slightly simpler. So this is this part here. The voltage is equal to the current flowing through it times the resistance. So we've just said we don't know what I is, we're trying to find that. So I've said I multiplied by 4.7k plus 0.j ohms. So I've converted that straight into its rectangular form. So it's a real part with no imaginary part. That's the expression for the voltage across the resistor. For the voltage across the inductor, we follow the same procedure, but it's a little bit more complicated. So the voltage across the inductor is going to be I times the complex impedance of that inductor. So it's 0 plus omega L J. I've just put J at the end. J is normally at the beginning in this expression. So it's 500 times 20 times 10 to the minus 3 because it's 20 millihenries, which gives us a value of 10J when we work it out. So I've just tidied it up in the next step. That's all I've done. I've just written I is equal to 0 plus 10J. That's the value for the voltage in the inductor, plus I times 4.7K plus 0J, which is the voltage in the resistor. So we can just pull I outside of the bracket and express I as I times 4.7k plus 10j is going to be our voltage. So let's rearrange and find I. That's what we've done here. So the source voltage over the two voltages through the resistor and the inductor, then converted this into its polar form here. Then you do the polar division and you get an answer of 6.3 times 10 to the minus 3, an angle of 0.12 amps. Because the unit corresponds to the magnitude, what I've done in the next step is I've actually said 6.3, an angle of minus 0.12 degrees milliamps. It just looks a bit tidier to me. It doesn't matter. Both of these are equally correct. However, this is the answer in polar form, so please make sure you do the last step and convert it back to the time domain, which is what you were asked for. If you don't do this, you will lose marks because you're not answering the question that you were asked. So I'm just going to put the cosine back in. So we pull the magnitude down. You know it's cosine omega t, which we've said omega is 500, minus the phase angle, which is 0.12 degrees milliamps. So that's the answer for part 1. Part 2 asks you to find the voltage across the resistor with respect to time. We know Ohm's law, the voltage across the resistor is going to equal the current times the resistance. We're going to do this in polar form because it makes life easier, because we've got multiplication. So let's go polar form. If we've got an addition or a subtraction, we're far better off working in rectangular form. So we've got a value for the current, we've just worked that out, so I've just pulled this value of the current and put it into here, times the polar version of the resistance. Do that multiplication and we get an answer of 29.61, an angle of minus 0.12 degrees volts. So then convert it back into the time domain, so put the cosine omega t back in. And as a double check, we can see that the phase of the voltage minus 0.12 is the same as the phase of the current flowing through it. So that obeys civil, so that's a good double check to make sure you've got. Okay, part 3, we're looking for the voltage across the inductor, VL of t. Once again, we know that the voltage of the inductor is going to be equal to the current flowing through it times the reactance across it. Remember, this value is in ohms, so it's kind of similar to resistance. It's just got a complex component. So we've put the current in its complex form, and we've put our reactance in for the inductor in its complex form. So where did this number come from? Well, back up here, we saw that the reactance was actually 0 plus 10j. So we know it's a magnitude of 10 in the j direction, and j corresponds to positive 90. So that's where that came from. Do that phasor multiplication and we get an answer of 0.063 at an angle of 89.88 degrees in volts. Finally, convert that back into the time domain. So put in the cosine omega t, and that's your final answer. So far so good. That's stuff we've all done so far. We did that earlier, so hopefully that should all make sense to you. I've missed out, I haven't gone into it in such detail as I have in earlier problem sheets, because you should be up to speed where you can do that now. So that's part A done. Next up, we're saying at time t equals 5 milliseconds, find these various values for instantaneous power. So how do you go about finding this? First up, we're interested in the instantaneous power in the resistor. Right, let's try and explain this in a nice slow way. The important thing is that the instantaneous power in anything is going to be equal to the current flowing through it times the voltage across it at that moment in time. This is our expression for our instantaneous power. We know what the current is because we worked that out. We also know what the value of the voltage across the resistor is with respect to time, because we also worked that out in the previous step. So what I've done is I've just introduced these values. So I've put in the current there, so it's 6.3 cos 500, which is omega. This bit would be t. What I've done is I've replaced t with the actual value of t, which is 5 milliseconds. So that's why it's 5 times 10 to the minus 3, and then minus this phase shift, and this is in milliamps. So that's the first step, to put that in. Our next point is I've put in the voltage across the resistor with respect to t. So this is 29.61 cosine 500, which was omega, t, which I've put the value of t in again, minus that phase shift in volts. So far so good. That's our first step to solving it. Next up, we need to calculate, I've done a couple of things. First up, I've moved the milliamps across to here because it represents the magnitude. So that becomes 6.3 times 10 to the minus 3. In the cosine bit, what I've done is I've done 500 times 5 times 10 to the minus 3. So this is our value of omega t. Remember, this is going to be in radians because we had radians per second, which was omega, times seconds. So we end up with just radians. We need to convert this phase shift from degrees into radians. So do that conversion on your calculator. Remember, it's plus minus 0.12 or minus 0.12. So what I've done here is I've just converted it into radians on my calculator. So that gives us minus 2.094 times 10 to the minus 3. And note you need to do the same with the voltage. So this was omega t, 2.5, and this phase shift here, which hopefully you'll get the same number out. So what have I done now? I've got the magnitude times the cosine of this is what the answer is, times, remember this was the multiplication we had, so this is the multiplication that's here, times the instantaneous voltage, which is 29.61, times that value that was here. So that's that bit. If you just multiply these numbers together, you end up with 0.12 watts. So we've put in lots and lots of different things. We've got something that's really quite simple out. So the answer is that the instantaneous power across the resistor at time t equals 5 milliseconds is 0.12 watts. So part 2 is asking us to do the same thing, this time for the inductor. So you'll notice quite often we do the resistor first, then we do the inductor, because we do the resistor first because it's normally a little bit simpler because we don't have this imaginary part. So let's have a look and see how we do this one. Once again, instantaneous power is equal to the instantaneous current times the instantaneous voltage. So we're just going to put that expression in. So what I've done is I've just put the instantaneous current straight in, because the current that flows through them is the same because it's a series circuit. So I haven't done all of this multiplication again. I've just pulled my number down from the previous part where we've done all this hard work already. So that's the same there. Right, then we introduce the expression for the instantaneous voltage across the inductor, which is 0.063 cosine omega t, put your value of t in, plus this phase shift which was in degrees. So what we need to do is this is omega t, 2.5, and then we've converted 89.88 into radians, which becomes 1.569. You can then add these together and take the cosine. So if you do that, I've just added an extra step here, what you get is 0.19 milliwatts. So that's quite a bit smaller. There we go. So next up, let's look at the instantaneous power in the source. You'll notice I haven't actually said which direction these are in, because actually part 4 is to state if it's dissipating or supplying power. That's why it's presented in that way. So next up, the power by the source is equal to, instantaneous power is equal to the instantaneous current times the instantaneous voltage. However, because we know this is a source, we need to make that voltage negative, because we know that the source is supplying voltage. That's an important distinction. So what we do, the instantaneous current, I've just pulled that number straight down. That's what we had up here, just to save doing that calculation over again. And this time we're putting the expression for the source in. So we know it's minus 30 cosine omega t, put the value in, plus 0 degrees. So we get minus 5.05 milliamps times minus 30 times minus 0.8, which gives us minus 0.12 watts. So that's the answer for that, and you'll notice it's negative. So when we go on to answer part 4, once the state of the components above are dissipating or supplying power. So let's have a look at this. What we can see is, if you look at the sign, it will tell you what's going on. So for the resistor, it's a positive value, so we know it's dissipating power. That's good. Resistors pretty much always dissipate power. The inductor is also dissipating power because this also has a positive sign, although it's a smaller value than the resistor at this instant in time. And we know that the source is supplying power because it has a negative sign. The current is negative. So when we found this out, when we worked out the instantaneous value of the current, we actually found it was negative. It was minus 0.505 milliamps. The reason for this is because it's an AC circuit, so the current can flow in both directions. All this means is the current is flowing in the opposite direction than that shown on the diagram in this instance, this very instant in time. So let's look at that diagram. Here we had it. All we're saying is that at 5 milliseconds, it's an AC circuit, so current can go both directions, is that it's actually going the other way. That's why it's minus. So there we go. Okay, finally part C. So part B was the meaty part of the question. Now we're going to just finish up with part C, where you're asked to find a single complex impedance. So the way we do this, it's quite a simple one. We can see that these are in series, so we can replace them with a single component. Calculate the reactances, We've done this already. We've got 0 plus 10J for the inductor and 4.7K plus 0J for the resistor. Just add them together to get the total, and that's 4.7K plus 10J ohms, and that's in rectangular form, which is what we were asked for. So hopefully you got all of that, and if you managed all of that, you're well prepared to face exam questions on that topic.